Okay, for part 2, we're looking at the reflection of sound, the refraction of sound, and how natural frequency and resonance work. Okay, so let's go look at this. And so first of all, there is this idea that sound will reflect. We think of light reflecting, but sound reflects also. That's why we get echoes. And so one of the rules about reflection of sound is that the angle of incidence equals the angle of reflection. And what does that mean? Well, what that means is that, so here's some sound waves coming out of a speaker here. And so the idea is that those waves, when they hit the wall, that would be the incident wave. And it reflects off the wall. That's your reflected wave. And the idea is that the angle is the same. So for this one, now the angle, you don't measure it to the wall. Instead, what you do is you measure it to a perpendicular line to the wall. And so in that case, this might be 30 degrees, and this might be 30 degrees. The angle of incidence and the angle of reflection should be the same. And so here, again, draw a perpendicular line to the wall. And so there, the angle of incidence should be like 45 degrees. And the angle of reflection, 45 degrees. Okay, so incidence and angle of reflection should be the same. This is why sometimes when you go to the symphony or something, you might see reflective panels up in the high part of the ceiling. Now this ceiling here is very high because they have this big pipe organ back here. And so probably a lot of sound was going up and getting lost up in the ceiling. So they added these reflective panels. And the idea is that if you can see a musical instrument, then you will get more sound from that instrument. So like if I could see the piano, then that means that sound from the piano is reflecting to where I'm sitting. Now, sound will be coming straight from the piano too, but the idea is you get a little extra if you can see it in these. The path of light and sound, they both would reflect the same. So if I can see the piano, I'll get more piano. If I can see the cellos, I'll get more cello sound. When I was a kid, they put these in an orchestra hall near our town, and they made them look like clouds. Okay, so that was cute. White clouds. So refraction is when the sound or light will go from one material to another, or material that has different properties, or just different properties. So we have water here that is deep and shallow. And so same material, water, but the thing is the conditions change. And remember we talked about how waves will slow down when they are in shallow water. Okay, so the deeper the water, the faster they can go. But when it's in shallow water, the wave will drag against the ground. So it goes more slowly. So that's what's happening here. So here we have a wave coming in, and these are the wave fronts. So like all the peaks are coming in together. And when they reach the boundary between the deep and the shallow, what happens is that the waves over on the left side of this wavefront start to slow down, whereas the waves on the right side of this wavefront can keep going at faster speed still at that up to that point because it's at an angle. And so what happens is that it changes the whole angle that they're at, the wavefront, because the ones on the left are slowing down, the ones on the right are still going fast, so they get ahead. And that changes the angle. So you can see how the angle, maybe it was coming in at an angle of, let me find a drawing tool. So to the perpendicular, if I drew a perpendicular line here, that's a really, really bad perpendicular line. Maybe it was coming in at an angle of 30 degrees, but it's leaving at an angle of only like 20 degrees to a perpendicular. So it has changed its path by 10 degrees or so. Now, so that's one thing. The angle of incidence does not equal the angle of refraction, unless, of course, it's coming straight on. So here you can see this wavefront is moving perpendicular to the break between deep water and shallow water. And so the wavefronts don't change direction. But what does happen is they do still slow down. And because of that, you can see how the wavelength changes. Right? You've got a larger wavelength here, you've got a smaller wavelength here. And that, remember, has to do with the idea that the wavelength is going to be equal to the velocity divided by the frequency, right? From our old friend, velocity is wavelength times frequency. So what happens is if the velocity changes, but the frequency stays the same, those wavefronts are still hitting at the same time, right? The same period is still between them. But what happens is that the wavelength would have to adjust. Okay, it can't go as far, it's going slower. So your wavelength gets smaller when it goes slower. Okay, so that's what that's about. This one shows how it happens coming backwards too. So it's going from slower to faster, and you can see how the angle changes hugely here from, it was about 40 degrees, and now it's closer to 65 or so. So anyway, so yes, the wave, again, it's a bigger angle in the faster water here, and a smaller angle in the slower portion. So anyway, we'll be looking at this more when we get to light. But right now, you merely have to understand that waves will change their direction when they hit a material with a different characteristics. Okay, so what happens is that this will happen for sound waves when there is a change in the air temperature. So let's say there's some houses here. And so when this guy's playing his trumpet, normally, if you have like warm air on the ground, but cool evening air moving in, that trumpet will go up, float up above the sleeping dog. But in the morning, when there's cool air on the ground and warm air moving in, then what can happen is that trumpet can float its sound right over the house and hit the sleeping dog. Okay, so it curves over. And so you can test this out yourself. Go outside in the morning. Don't blow your horn. But you can hear traffic from further away. It's much noisier in the morning than it is in the evening when it's all quiet and calm. And that has to do with sound refraction. And so this happens when you're camping too, especially if you're camping by a lake or something. The mornings are so noisy. You can hear every camper, especially the ones with RVs. They're slamming their doors. They want to be up at 6. You want to sleep in. It's almost impossible when you're camping to sleep in. There's sunlight in your face and there's noise all around you. And at night, it's much quieter. Okay, and also refraction has to do with the way that a dolphin can focus its pulses of sound that it sends out to find fish. So what happens is that the melon, so that round shape on the dolphin's head, that's called the melon. It's a lump of fat in there, some oils and stuff. And so basically the dolphin blows its nose, okay, it snorts, and that turns the ultrasonic frequencies, and those are refracted inside the melon, just like eyeglasses refract light and focus it. Then the melon refracts the dolphin's snort, and that keeps it a focused sound, so when it reflects off the fish, the dolphin can tell what direction the fish is in. So the melon is a lens for the dolphin's ultrasonic sound. Okay, now objects have natural frequencies that they make. So like we talked about drums. And if you change the tension of the string, so if you tighten these strings here, that will tighten the drum head, and that would make it have a different sound, right? A higher frequency if you tighten the tension. So it depends on the materials also. Is this goat skin? Is a cow? For a xylophone, right? You can have a xylophone made of wood or of metal. And so the dimensions matter, right? So for a xylophone, deeper notes here, higher notes where it's smaller, right? So just like the drum head, the smaller it is, the smaller the wavelength that you fit across. And that means a higher pitch. So objects will have natural resonant frequencies. A piano has many strings of different lengths. And that's one reason the best pianos have this curved shape so that they can resonate in many frequencies. So objects can change the resonant frequencies by placing them under stress, so tension, or making the size of the resonance chamber different. So for a bottle, so when people do wine glass, they put water in or wine, and then by rubbing your finger around, you get different frequencies from the differently filled cups. And what's going on with a bottle, if you've ever blown across the top of a bottle, which you should definitely do in your life, when your water level is low, then the wavelength that fits in there, it could be this big. But when you fill it up higher with more water, then the wavelength that fits in is going to be smaller. So you get a higher pitch. So anyway, go practice your bottle floating. Musical saw is an excellent example. People actually play them by placing the saw between their legs, an ordinary type saw, and they play them with a violin bow. And the thing is, they adjust the tension by bending it. So she's using her hand to bend the saw. That changes the tension, and that changes the frequency you hear. So anyway, musical saws, watch some on YouTube. It's a weird sound, sort of sound. Anyway, very strange, very high pitched usually. Okay. Now resonance, that word refers to the idea of objects resonating at their natural frequency, but also you can resonate with other things. So when you're pushing someone on a swing, it has a natural frequency because of the length, right? It's a pendulum. So the length is its natural frequency. And when you push on that to make a person go higher, what you're doing is matching that natural frequency, right? You don't just stick your arms out at random times. No, you stick your arms out when the person comes towards you, when the kid is coming towards you, and you push them back the other way when they're ready to go back. So you're matching the natural frequency. And you can increase the amplitude of the vibration by matching it. And that's called a forced vibration, is when you are adding successive impulses are being applied to the vibrating object in rhythm with its natural frequency. So this can actually happen with a tuning fork, where you can have another tuning fork off to the side here, sending out pulses. And if the tuning forks are matched in frequency, then those waves will reach the tuning fork and push it in and cause it to actually start vibrating, even when even though you're not touching it, it will end up making sound. So let's go see an example of that. Okay, so sticking this over here. Okay, so I've got a couple of tuning forks here that are matched tuning forks. And what I'm going to do is hit this one over on this side and cause the other one to start vibrating also. Uh-oh. Okay, so gonna whack on the left, make the right one play. Oh dear. Let's try this again. Okay, now make this one quiet. Do you still hear the sound of the other one? This one is playing. Let me put you a little closer. Try that again. Okay, so. Okay, so you might be able to hear the second tuning fork still humming away. Now, another place where resonance, see there are some weights back here on a spring. So we were talking about how you can have an equilibrium position. Yeah, let's move a little bit more power. Okay, so an equilibrium position might be around 7 here, and as I pull it down to 8, then when it bounces up to 6, so its amplitude would be 1 inch either way. Okay, but it has a natural resonant frequency. Now, if I match that frequency by hitting on it at that natural frequency, I can get the amplitude to increase until I can actually explode it and scatter pieces across my desk, which I'm not going to do. Anyway, but the idea is I was able to add energy by matching the frequency. If I just hit at random times, then I'm not going to get it to add, right? I'm not getting it to go greater amplitude. I have to match its natural frequency and add energy at the right time to get a large amplitude change. Okay. So, all right, now this can happen like in a factory. Sometimes the floor will start vibrating when you have heavy machinery running. A great example is if you're going to go to the Renaissance Fair, do that. If you've never gone to the Ren Fair, which is up by almost to Wisconsin, right on the border between Wisconsin and Illinois, go to the Ren Fair. It's open again, okay? So go have fun. Just go watch people yell jokes at the mud pit, and it's just wonderful. Once you get in the gate, there's all sorts of shows to see for free after that. And there's, of course, food to eat, which is not free, and things to buy, and tournaments to watch people jousting. And you don't have to wear a costume. But anyway, it's just a great place to go. And lots of shade, because they have lots of beautiful, tall oak trees to shade you. So anyway, so go to the Ren Fair. Anyway, but when you go there, there's a bridge across a pond. It's one of my favorite things is to go across this pond, and if you save some bread, you can feed it to the turtles that are there and the fish. And so anyway, but as you walk across this bridge, it bounces, and it has a natural resonant frequency. And as people walk across it, they will start bouncing to this natural frequency. It's great fun. And you can make it get higher and higher vibrations by, of course, moving up and down with the bridge. In your car, sometimes parts will start to rattle, old cars especially. The old parts start to get loose over the years, so your glove box will rattle, or a mirror or something will start to rattle at different speeds because you're going over bumps on the road. And that's a type of resonance too. Okay, so one of the videos that you have to watch is the Tacoma Narrows Bridge collapse. Anyway, the idea with that is this bridge was built to withstand winds of 90 miles per hour. And instead, what happened was that it was hit by winds and that were only 40 mile per hour. But what was happening was that it was pushing the bridge, and you can see how it's tilted here. It's not supposed to be like that. And so the wind was pushing it and swirling around the edge, and that's called vortex shedding. And those vortexes were pushing on it like you would push a kid on a swing. And the bridge was going wilder and wilder in its swings. And eventually it broke down. There was one fatality. It was a dog who they couldn't get out of the car. People tried, but he bit people. Okay, so anyway, so go watch that. There's a link in the module. Okay, now, so usually there's a bunch of videos we watch. Oh, and so here's some words by Theodor von Karman, who was the first person to put an object like a bridge in a wind tunnel. People have mostly just done it for airplanes and stuff before that, or cars. And he said, let's see what happens to a bridge. So they were able to get it to oscillate in the wind tunnel. And some other videos to watch. There's Wine Glass Resonance with Slow Mo Marty, and that's really good. And then there's Rice Resonance. When you're watching this, what these are just metal plates that gets vibrated at different frequencies, and it makes these cool patterns. But it's rice or salt that you put on top. And what happens is that the areas where the salt stays, those are the white parts, basically those are like the nodes because there's very little motion there. So waves are being sent out from the center, reflecting back, and some places they cancel and some places they add up. So you basically end up with the black parts are antinodes and the white parts are nodes, but it's two-dimensional. So you end up with these crazy great patterns on these plates, which are called Chladni plates. Now, a sadder example of resonance in action is when the earthquake hit in Mexico City in 1985. And this was an 8.1 earthquake. And unfortunately, Mexico City is built on an ancient lake bed, which makes the ground very soft. Also, it's in between mountains. So what happens is that an earthquake gets in and starts reflecting back and forth between the hills in that soft soil. So it's a very dangerous spot for earthquakes. But they've rebuilt the city much better since 1985. So the last time they had a big earthquake, there were some fatalities, but not as many as in 1985. But what people discovered in 1985 is that you would have buildings standing right next to a building that has collapsed down. And so it wasn't the location, it was the buildings that were causing the problem. And they found out that the buildings resonate. So if the buildings have dimensions such that the wavelength that they will sway at, for instance, is the same as the earthquakes, then that building will fall down. Unfortunately, earthquakes have lots of different frequencies and wavelengths, so we can't, unfortunately, just build buildings that will never match the frequency of an earthquake. But what they do instead is they try to make sure that buildings have lots of different dimensions, so that that's one way of doing it, so that they don't have all parts the same dimension. So their X, their Y's, their Z's aren't all the same. And that way, they have lots of different frequencies. So the whole building, so if you have a building that's very square, where all the floors are the same height and the same depth and all that, then those are very susceptible because that means they have maybe just one frequency, easier to shake down. So instead you want different dimensions, and there are lots of other cool tricks to figure out how to make buildings less susceptible to an earthquake. But the resonance idea, that came about because of that 1985 earthquake. So usually I offer an extra credit paper. So you can earn extra credit by writing a paper on 3 methods for building earthquake-proof buildings. So that doesn't mean earthquake-proofing your home, like attaching the bookshelves. No, what we mean are what can you do with the building? What does the architect do to make them earthquake proof? Anyway, so you can just cut and paste from the internet. That's fine with me. Throw in some words to join them together, put in some pictures, make sure it's not more than 3 pages, and you can earn good extra credit, okay, for showing me that you have found and read information about earthquake proofing buildings. Okay, so that's an extra credit project. All right, and so there is another video to watch, which is also linked in your module, and that shows these 3 pretend buildings. So you've got a short one, a tall one, and a medium-sized building. And they're on what's called a shake table. So this table shakes back and forth, and these are used in physics classes, but they're also used to test building models and for earthquake proofness. And so they have one that is bigger than, well, bigger than a classroom, like 30, 40 feet long. That is in Japan, they have a giant-sized one, and in California, they have a giant-sized one too. And so those are 2 places that are very concerned for earthquakes. And so they test models. So these are just little ones, and so it's fun to watch as they increase the frequency of vibration, which buildings will have more troubles. And again, relate to that idea that if frequency increases, wavelength decreases. And the wavelength depends on the dimension, right? Okay, so anyway, so make sure you watch that. Okay, and that's the end of part 3. So, or no, the end of part 2. We're going to go on to part 3 in a minute. Okay.